here. One is power generated by power plants. Artificially, we are generating power with some nuclear plant or coal or combined cycle, gas turbines, etc. And we have the power generation from the renewable sources. So power generated by the renewable sources are climate dependent. We have lot of constraints. Once a facility has been installed, we cannot increase it further. Once it is installed, it's installed. We don't have any feasibility to increase it further. So only control what we have is based on the load demand, we can vary the power production at the plants. For example, if we are generating power at some renewable facility, and we are generating power at the power plant. Okay. So, and we have the power consumption at home. What we can do is we can do the data acquisition, what are all the power consumptions happening at home side. And one is the general appliances, what we have electrical appliances, that's common in all houses. And there are few appliances based on climate like air condition in summer and room heaters in winter that can be acquired separately. And if the data is being stored with the classification based on the power consumption on the daytime and based on the climate, if data is stored in this form, then we can do the data analytics based on what will be the power consumption at the daytime, and based on this the load distribution can be happen between renewable sources and the power plant. For example, what we are considering as of now is power generated at home is not sufficient to run all the appliances available at home itself. So we are dependent on the power supply from the external sources. So if we have the facility, then we can calculate how much energy is generated by the renewable sources, and also and based on this parameter, if we could calculate how much energy to be produced from the power plant, that load management can be balanced in that way. So if storing the data based on the daytime power consumption and based on the climatic power consumption, I think we can optimize the best way to utilize the best of the national renewable energy sources, and with this what we say power production done by the artificial or non-renewable sources. So I think this form of architecture is better to plays better role to optimize the power needs. Thank you. So this was a small idea how to optimize it.
Thank you. What is your name?
Arun Rashid.
Thank you, Rashid. You provided a very good overview, and I can understand that, his enthusiasm and understanding of the complete system. What he provided at very high level, that to overcome the intermittency of the renewables, how we have to manage the conventional power plant, and for that how this home energy management system, or maybe in a simple way, load patterns can also be modified accordingly. That is basically the key or high level theme of the project which I was discussing with you. And what Rashid was telling here with reference to the power plant and the renewables, I teach one very focused course, Power System Dynamic Stability and Control, in which I use this one. So when we have these conventional generators, so how we have to implement control system, PID controller for controlling the input flow to the turbine with reference to this intermittency. And then of course, we can get the prediction of the intermittency. Conventional power plants are there, but demand side management demands are going to be fluctuating. So we can get the opportunities for demand side management. So it's really good. Anyone want to present something? Please feel free. Yes, you want? Yeah, please. Very good. Yeah, then no problem. So I think I will just. You can put. I think that maybe that side HDMI. Yeah. It's really good. I am very happy to see that active engagement from the participants, because that is always good, na? Otherwise, it is just like a one directional information flow.
Good afternoon, sir. Thank you for providing me this opportunity. I thank Farooq sir also for conducting this event. Power management system, as you explained, I came to know that hydrogen power also plays a major role in providing power for households as well as for industries. I categorize power management system into mainly three, depending on location, season, and usage type. Usage type is nothing but household or industrial use. Because those two plays major difference there. Now, depending on the season, depending on the season, the power uses will be varied at vast during winter season or summer season or rainy season. There is a lot of change in power uses, as well as depending on the location also. Coastal areas require different power uses, whereas the central regions need different power, and hill regions need different power uses. It's not that one power management system is created and it can be utilized for all centrally, for all locations, or for all the seasons. It should be changed depending on industrial as well as household. So I categorize this power management system that should be designed into these three categories. Now, in this again, we can use machine learning for making the decision which location we are going for, whether it is urban area, coastal area, or rural area, where you want to use it. In those areas also, depending on the season, you also have to compute the values, how much power consumption should happen. This can be achieved only by using machine learning, where we gather the information or data from those particular locations regarding the season as well as uses, and as well as the maybe the power consumption assumption that can be calculated by using machine learning. This machine learning plays a vital role in making this decision. And now once we make this decision, you can also come up with which type of power should be, generation should be used, whether it is a wind or hydrogen or solar cell. Because when you see coastal areas, wind, we can go for wind. When we are going for hill areas, we can't go for solar. Mostly wind as well as solar also you can use, but not hydrogen. In urban areas, we can mostly go for hydrogen. We can't go for wind. Depending on those areas and locations, we can decide which one we have to use. And it's not that we have to use only hydrogen for urban or wind for coastal and remote area solar. You can also have a hybrid system depending on the usage type there. If industries are located in urban areas or rural areas, the power consumption will be completely different. Depending on that particular usage only, we have to recategorize that. So you have to create a hybrid system where we can go with wind, solar, hydrogen. All three combination can be used, or any two combination can be used, so that a continuous uninterrupted power can be produced and supplied to the industries or the people that they are living. That's it. Thank you very much for your insights, sir. From your insights only I have created these slides.
Very good, very good, very good.
Thank you, sir.
So,
if I made any mistake, please sorry, sir.
no. I mean, it's really very good to understand that how the participants, they are thinking from different point of view. For example, she thought, it's okay. She thought, let's say, how this machine learning tools can be useful for decision making. So that is a really useful. And that machine learning tools, when we have this unpredictable or intermittent, nature dependent, renewable energy sources, then most of the time, like physics based control system may not be in a position to take the decision. We need to have some prediction. So what her conclusion was that, so machine learning tools can help us in making the appropriate decisions for doing this proper operation of power management within this hybrid energy system. So thank you very much. And then of course, maybe I believe that you are in the academic profession, you can find out some good topics and give it to your graduate and undergraduate and postgraduate students for doing their project work also. So, thank you. Anyone among you want to come forward and to share something? Please feel free. Anyone? From the back side, anyone want to say something? Okay, so don't worry. So I will carry on further and I will share with. Yeah, don't worry. Okay, so before the break, I was talking about how we have to do the system architecture to integrate the front end system and the back end system, and I requested, like, based on your mind or based on your thoughts, how we can have that architecture. Now here I am going to present you the architecture which have been implemented in this project. Now here you can understand that how this front end system and the back end system, they have been integrated together. In the front end system, we have the home energy management gateway, and here you can see that this home energy management gateway, which is basically of the size of our mobile, it has the operating platform OGEMA, and this gateway basically going to work on controlling the operation of non-critical power intensive load based on the input which it is going to get from the back end system. So, in this platform you can see that we need to have the input output provide drivers also, and of course, here we are going to select some of the appliances, those are non-critical power intensive. We cannot select all the appliances. So, when we are selecting some of the appliances, let us say we are taking thermal inertia based load or the boiler, in which our complete mathematical modeling or of that boiler will be required, okay, because that boiler has some constraints for minimum operating temperature, maximum operating temperature, its input power, as well as from its output how much water we are consuming. So, that modeling is going to be required and going to be integrated in this home energy management gateway. So, this home energy management gateway is going to be helpful for the local provisioning also. Now, what is going to happen here? You can see this home energy management gateway has to operate based on the schedules which have been received from the back end. So, here you can see the schedules are communicated here, and then based on that particular appliances have been covered here. But if you at the same time you can see that here lot of measurements of the system components is going to be there, okay, and that measurements and the reports going to be communicated through some communication medium to the backend system. In the backend system, we are treating as a virtual power plant. So, here you can see that continuously this front end system is providing information of the measurements and the reports, let us say, to the backend system, okay, and then backend system is going to use all those measurements and the reports. Then at the same time, the information from the home energy management gateway is also sent to the flexibility forecast, because our objective is to do the flexibility, and for doing the flexibility within the distributed network, here we are taking the aggregation of households, right. We need to have the key component that on forecasting. So, this flexibility forecast, right, can help us, right, how much energy profile or the load profile of this particular house then getting aggregated is going to be there, and that will be used as an input to this virtual power plant. Now, you see here we are talking about one system or one house, but we are going to have n number of houses within that cluster. So, here aggregation is also very important. Then based on that, here this SEMIA intelligence or this project intelligence, where I was giving most of my technical focus, that how we had to do the real time scheduling of the loads within on the front end system, but at the same time considering the distributed system operator grid constants. So, that grid constants is going to be used here for developing the real time scheduling of the demand side management, and for that then of course, we will need some algorithms also. So, me and my team, we worked very heavily in developing this algorithm. One was centralized and another was decentralized, and then based on that algorithm, considering the grid constant, taking into the flexibility forecast output, then this virtual power plant can generate the demand side management scenario one day ahead or maybe 15 minutes ahead also, and then going to communicate to this home energy management gateway. Now, here you can see that how this architecture, like many of you I believe that from computer engineering background, electronics background. So, they may be in a better position to understand how this architecture is going to work, right. So, this is a very interesting thing. So, here on the front end side, when we are getting all this information, like, and this has been processed through this home energy management gateway, and then at the same time we can also have some mobile application also or mobile app, in which then we can collect this information from the home energy management gateway to see that how our energy consumption profile is happening and how we are reducing or how we are getting the signals from backend system here, and how the user's load profile is happening. Then at the same time, here also one more point, that based on the real time energy pricing, this user may be in a position to know that, because here we are getting the scheduling pattern and we are shifting the operation. So, the incentive for the customer is that how much energy bill saving is going to be there, that can be seen through this, let us say, some gateway here. So, very interesting to see here, we are having the front end server also, right, where we only the local data of that particular house. बैटरी इशू है हो वही मेरे को लगता है चार्ज कम हो गया होगा उसका आई थिंक सो विल सी हाँ लगा हुआ है हो जाएगा आ जाएगा सो एनीवे लेट द लैपटॉप गेट चार्ज्ड और re-energized. We need energy also, so laptop also need energy. So that with that architecture in which you have seen very clearly how that front end system and back end system, they have been integrated together, and how these prediction techniques are going to help to the back end system for taking the decision in developing some demand side management scenario. And do you think that your thoughts was matching with this architecture? So, till it gets fully energized, I will explain you. In this project, 100 houses from Norway and 100 houses from Switzerland, they were selected. Within these 100 houses, home energy management gateway were installed. This home energy management gateway were provided by one of the partner, Devolco Products from Denmark. And in that gateway, Ogema platform from the Fraunhofer, Germany was also the partner. That platform have been installed. And using Devolco Products components, Zigbee communication were installed with this boiler load to communicate the information between the gateway and the boiler. And then we have seen the backend system. In the backend system, the virtual power plant was there. That virtual power plant, it was located in Germany. Now you see how the different geographical location were integrated towards for doing local demand side management. And that backend system or the virtual power plant, it was operating based on AC microgrid architecture or with AC Drupe functionality. This virtual power plant was in a position to get the information of renewable energy production in that particular region where the system was connected, if it is any there. Based on that, giving that priority to the renewables, okay, and considering the predicted load profile of this aggregated households and taking into account the grid constraints even at the feeder level, then this backend system used to generate the demand side management scenario, and that demand side management scenario was communicated to the front end system for shifting the operation. So, you see how complicated it was, and I have a lot of results on this project also. So, let us see how I can share with you. So, it is not getting, we will wait for some time. So, then second point, which is again very important to you, is that when we are doing this communication of the data, we have to consider security and privacy. The mobile operator which we used in this project, they were saying that the data is quite secure and encrypted. But you might have seen that there was one work package on data security and privacy. We hired one ethical hacker as a postdoc researcher and who worked on this project, and he was in a position to hack the complete system, and using this signal he was in a position to switch off some of the loads of one of my colleagues' house also. So, that house was without hot water for couple of days because we were testing that system, and that my colleague, he was on holiday at that time, right. So, you see how data security and privacy is going to be important in the smart grid system where we are using information communication technology infrastructure, and that will be required for our machine learning algorithms also. If suppose someone is hacking and injecting the false information, so machine learning techniques or any prediction techniques are going to generate bad scenarios which may impact the operation of such type of system. Is it okay? So, then another data security and privacy point was within this OGEMA platform also. When this OGEMA platform, right, basically it is also receiving the information from the backend system, but it has to communicate that information locally where we use ZigBee communication. So, we have to see that from local home energy management gateway to this ZigBee component, the data which we are sending or the signals which we are sending both in bidirectional manner, right, how secure it is. If suppose we are using such type of system in any house or in any industry, and if suppose some bad person is there, may be in a position to hack that information and to impact the operation of such type of system. So, here the conclusion is that while doing the machine learning techniques, we have to be very careful with reference to the data which we are collecting, whether it is the real data or injected data or hacked data or all these things. And then of course, we will need security and privacy of the users also. If we do not take into account the users privacy, so that is also not very good, because in Europe or in many of the countries, user privacy is taken on top priority. Good. So, now you got the idea that how critical it is, right. So, of course, you see how we have to offer the schedules from intelligence to here, then that schedule has to communicate it here also. And then another very interesting thing, that how this information is going to be useful from the transmission system operator point of view for making our network more sustainable also. So, I believe that you got some idea from this architecture, right. And here in this project, design and implementation of the flexibility forecast service at Fraunhofer, Germany, and the subsequent integration with the virtual power plant have been done. Okay. So, that is a really interesting, and because it needs lot of efforts also, but we have very limited time and diversified participants, right. So, it is not that easy just to go in depth on each and every technical point, but you are getting some idea that is important, and then some of these ideas then you may implement through your students, through some project works also. Then another thing which we noticed here, great constraints. While developing this architecture and sending the demand side scenarios in which we need to consider the thresholds at feeder and the household levels also, because every house is having some certain peak demand. So, we have to be below the certain peak demand. So, that also we need to consider. And then in such type of system where we are using machine learning or forecasting techniques for making the decision, security and privacy going to be very important. That is why there was one dedicated work package on security and privacy also. So, in this virtual power plant functionality, first we integrated the built in stochastic scheduling mechanism. This stochastic scheduling mechanism can be replaced with any other machine learning techniques also. And we made possible that in place of this stochastic scheduling, we can allow the third party schedulers to network with the household clusters and integrate with virtual power plant. So, here the front end system and the back end system working is really important, okay, with interworking of DSO grid constraints and the constraints with virtual power plant. Constraints with virtual power plant is that we have to promote the renewables, at the same time we have to take into account the conventional power plants constraints, so that this virtual power plant can generate the demand side management scenario using group functionality. Okay. So, here you can see that what the input data is going to be required for the scheduler for developing probabilistic schedule for each household. So, here you can see that the input data which is going to be required, like energy pricing, because I mentioned that is a real time energy pricing is going to be there, grid constant is going to be there. We have to consider in this case probabilistic flexibility forecast. So, that information we need in the scheduler also. So, in the scheduler then we can create with the help of the stochastic development scenario constructions and reductions also. Then it may develop n number of scenario. We have to do the optimization of those scenarios also, which scenario is going to be useful. So, here you can see that not only creating the scenarios, but we have to optimize them. That also has to be done in by using deterministic optimization process, and then we will do the optimization, and then that optimization can create some schedules for each scenario and n number of schedules, and then that schedule based on those houses, right, going to be communicated to each households. So, here you see it is not going to be as simple as we are thinking, and if we go back, for example, here on this slide, if you simple way we think, we have to shift the load here. So, just we put some small program and we can do it, but is it like that? No, it is very complicated, and we need to have virtual power plant facility, front integration of front end and back end system, use of ICT infrastructure, we have to take care of the security and privacy, so on and so forth. So, that is why you can see that how unique this project it was, in which we received around 3.8 million euro for 3 years period. And in the first 1 year, we worked on developing all these scenarios, okay, and how it is going to be working and like that. And after first year, then we recruited 100 houses in Norway and 100 houses in Switzerland, and then we developed this hardware, and then before implementing that hardware in those houses, we need to do the lab testing also. So, that lab testing we did with a partner company Devo team, whether that system is working or not. Then after that, then we implemented or installed that systems in 100 houses in Norway and 100 houses in Switzerland, and then we tested this system. So, you can see that how the information exchange which need for the DSO service and data interface started, then basis for data model for grid constraints, data model for flexibility needed, and management interface between the SEMIA scheduler. So, here you see that we have this virtual power plant here. This virtual power plant I explained you in the previous slides, let us say, going to communicate algorithms. So, scheduling algorithms here, those scheduling algorithms are communicated to this houses. For what purpose? Demand response scheduler. Okay. So, here from the prosumer point of view or the consumer point of view, right, we are getting the flexibility and the shifting of our load with reference to the flexibility, right, we are contributing in improving the services of distributed system operator. So, this is a very, very interesting project which we have implemented in cooperation with 12 partners which we discussed earlier and implemented in Norway and Switzerland. Now, some of the things which may come in your mind also. I think I will just, yeah, that every house is going to be a very different consumption profile, different user behavior. Okay? So, it is not that easy. Some of the houses may have more leakage of the heat, some of the houses they may have been newly built. So, for that, to doing more detailed analysis which we did also, we need to have or we need to do the modeling of that house also. So, let me see if I can find that one here, if it is there. Yes, yes, it is there. You see, anyway, so you can see here how this household load categorization which we did, critical load, non-critical load, power intensive non-critical load, water heater, air conditioning, cloth dryer, electric vehicle. Then we developed the model for each unit, okay, with complete flow chart taking into account all equation, user preference, typical parameters and so on and so forth, and temperature, demand, different parameters, right. Similarly, for the clothing dryer, washing machine, electric vehicles and so on and so forth, then defined the critical load, non-critical load, then we developed this energy management system algorithm, like by defining the user priorities also, and then accordingly then energy pricing mechanism, time of use, real time pricing, demand charges. Then here you see with reference to different conditions, how much energy saving can be done, which load we have to shift and so on and so forth. So, lot of work which we did, right, but now we have the limited time and sometime is difficult for us also to cover all these things, but we have that all that work here. So, if in this GAN course, the objective is that to create your interest in sustainable technology, to use machine learning also, and I believe that we are trying, me and Farooq are trying our best to create that interest in you. Okay? So, here that this is a typical example of scalable energy management infrastructure project I am presenting. Then when I said that pilot testing, it was work package 8, how 100 houses were there, 100 houses were in Switzerland, then how we tested this system for taking into account thermal load and boiler. So, then the pilots concluded testing of demand response provided by the SEMIA infrastructure through virtual power plant. So, it means that the results what we got through this project is at the TRL level of 8, 7 to 8. Okay. It means that the system which have been developed by using all this components and configuration and like that is available for the industry to take it forward and get it implemented into the market. So, that is the TRL level 7 or 8. So, now you are, many of you are very young professionals and have a long career to do the research work or further work. So, you can think like whatever the research work you want to do, it should have very high TRL level, so that industry can get a benefit out of that. So, in future maybe when we will plan any another GAN course, we will try to integrate some industry together, so that we can get some industry inputs also, and we can also provide our academic inputs in creating more industry academia interactive GAN course. Okay. So, in this project several infrastructure components which you have seen were finalized during the period, and it includes basically the integration of back end and the front end system with grid constants, and the system level testing was conducted alongside the integration of SEMIA infrastructure, and most of the test cases have been successfully passed, and we did some security demonstrations also to see that what are the data security and privacy issues are there in such type of system, and we observed some vulnerabilities and we verified them and mitigated them. So, we tested this automated demand system in the first scenario of heating system or the boiler load, both in Norway as well as in the Switzerland, and then we got the feedback from European Union and the reviewers. Like here you are tested only 100 houses at one region, 100 houses at another region, but if suppose such type of system might have been implemented in thousands of houses, then how it will happen. Then we used the simulator from HESO Switzerland to test this system for more than 200,000 household simulation, how it is going to work. So, this is a very interesting project in which we are integrating all engineering disciplines together, including economics also, because such type of projects demand side management is going to impact the revenue generations of the utility company. So, they may need to have new business models there. That is why you might have noticed that there was one work package 6 or 7 in which new business models were developed using energy on platform from Switzerland. So, now I want to conclude here, we need to have sustainable community, and to have this sustainable community we need to integrate information communication technology infrastructure, and when we are integrating this ICT infrastructure, lot of data will be collected, including user preferences and the behaviors also. So, based on that, then of course, it is not easy to make the decision using physics based approach. So, for that we need to use machine learning or artificial intelligence based approach. Then only we can move towards the sustainable communities and to achieve our goal of sustainable technology development. So, thank you. Do you have any question or any feedback on this project, or what you have learned from this project that I want to see? Anyone among you can come forward and say that what is your learning from this project, because it is a very complicated project and the objective was very small. Objective was just to make the load profile simple or to improve the load factor. But when we have seen all this, right, then you might have noticed that how complicated it is going to be there. And this complication can be overcome through smart grid technologies. And to have the operation of the smart grid technology, we need physics based approach also, but at the same time we have to use machine learning tools for making decisions also. So, anyone among yourself want to come forward and to say something on this project? What? Yes, please, 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 please. Yes, this is a very good question. We have seen here demand side management scenario, and this demand side management scenario was basically going to be operate based on the grid constraints or maybe the real time pricing. With reference to the energy storage, if we are going to include into the demand side management, whenever there is a low energy pricing, we can store it, and when there is high energy pricing, we can sell it back also. With reference to this algorithm, what she was saying, so maybe in tomorrow's lecture, I will provide you active microgrid architecture, which we can use in charging and discharging processes of batteries, considering group functionality and those controller, what we will discuss tomorrow maybe, that you can even put it in a chip also and can work it. So, that will depend on two situations. One situation where we are using the energy storage as from the energy management point of view, one point. Second point, whether we are using power management point of view, because for both situation, the controller operation is going to be very, very different, right. So, in hybrid electric vehicles or in electric vehicles, the management of the batteries are mainly based on power management approach, because we need instantaneous power. And if we consider, let us say, from the domestic applications point of view, then that can be more on energy management approach. Is it okay? And for the batteries, then controller, it will be required bidirectional controller, right, charging and discharging. In bidirectional controller, if we are using the power management approach, it means that batteries has to contribute to instantaneously deliver the power, not from the energy management point of view. That time always we have to think like how much reserve in the battery banks we need to keep, so that they can contribute towards the power management service or ancillary services. Okay? So, maybe if time permits, in tomorrow's lecture we will discuss that. Is it okay? And then for controlling that operation, because human cannot do, it is going to be automatic, right. So, we need to use some algorithms, and to get that we need to have some prediction also, right, and all the time then we need to estimate using some prediction techniques state of charge level into the energy of the battery, then only they can contribute in that. And this state of charge, dynamic state of charge condition into the battery analysis is again very challenging. We will need equivalent circuit diagram of the batteries. That equivalent circuit diagram of the batteries is going to be changing all the time due to the degradation of them. Okay. So, that is also very interesting research work. Some of the PhD students in my university, they are working on that, and they are using impedance spectroscopy for modeling the battery banks under the different operating condition to know the degradation process also. And that model will be required in doing predictions of the available energy within that battery with reference to the time for contributing towards the power management, not on the energy management, mainly on the power management. Is it okay? Anyone? Anyone had any question, discussion? So now I will give floor to Farooq. Want to say something, Farooq? So